Hello everyone, my name is Vyshnav. As you can see on the screen, today we are going to discuss about symmetric key algorithms. Just imagine a world where everything you send online is visible to everyone. That is your bank account, your Insta password, your chat with your friends, everything. It's terrible, right? So we need cryptography. So what is cryptography? It is the study of communications and a form of security for messaging. Cryptography is used to keep messages and data secure from being accessible to anyone like hackers other than the sender and the intended recipient. The term is derived from the Greek word cryptos, K-R-Y-P-T-O-S, which means hidden. I think everyone heard of the word encryption. If you open WhatsApp chat, we can see on the top that message to this chat and calls are now secured with end-to-end encryption. So here, what is encryption? Encryption is a way of scrambling data or translating plain text into something that appears to be random and meaningless, which is ciphertext. Decryption is the process of converting that ciphertext back to the plain text. For example, if you observe, nowadays almost every website link starts with HTTPS. The S means the data is getting encrypted. Let's say I want to open a LinkedIn page. I'll ask for Google to open LinkedIn. The Google server has to reply me with the LinkedIn page. Then I'll type my username and password. And the Google server will check if it is correct or no. If it is correct, my LinkedIn page has to be shown on my desktop. This whole process of exchanging data is encrypted here. So the website is encrypting data at my side and decrypting at the server side and vice versa. So the hackers in between cannot see or sniff the data. They can see and sniff the data, but they can see only ciphertext, which is meaningless and random. So the website that starts with HTTP is not encrypted. So anyone in the network can see the data transmitting using tools like Vyshnav. Cryptography techniques are mainly divided into three types: symmetric cryptography, asymmetric cryptography, and hash functions. So what is a symmetric key algorithm? A cryptographic algorithm that uses the same secret key for encrypting as well as decrypting. It is also called as conventional, private key, and single key. Here, sender and recipient share a common key. That is, sender encrypts data with a key and the ciphertext and sends the ciphertext to the receiver. The receiver decrypts the data with the same key to get the plain text back. Here, keys are generated using random number generators or pseudo-random number generators. And the key is distributed using various key distribution technologies like public announcement, public available directory, public key authority, etc. All classical encryption algorithms are private key. Nowadays, we use symmetric key algorithms like AES, DES, RC4, etc. So what is a asymmetric key algorithm? Asymmetric cryptography is a process that uses a pair of related keys. One is public key and the other one is private key. The first one is to encrypt and the second one is to decrypt a message. Private key should be kept confidential and public key is generated using the private key. So a public key can be used to encrypt messages and private key is used to decrypt the same message. As here in the picture, we can see Bob wants to encrypt the data and send it to Alice. So here Bob takes the Alice public key and encrypt it and send the ciphertext to the Alice. So Alice with her private key decrypts the data and gets the plain text back. The same public key and private key concept is used for digital signatures also, but it works the other way around. Private key is used to sign the document and public key is used to verify the signature of the document. There are some misconceptions about asymmetric key encryption, like asymmetric encryption is more secure compared to the symmetric encryption. No, but the truth is the security is based on the key size. If the key size is more, it is difficult to brute force. And another misconception about asymmetric key encryption is it made the symmetric encryption obsolete. It is not true. Because of the computational overhead of current public key encryption schemes, it is impossible that symmetric encryption will be abandoned. So basically, asymmetric key encryption is used to share the keys of symmetric encryption. We can characterize cryptography system by way in which plain text is processed: block ciphers and stream ciphers. Here, symmetric algorithms are two types, like block cipher and stream ciphers. A block cipher is a symmetric algorithm in which it encrypts a fixed data block using a key. Examples are AES and DES. In stream cipher, it encrypts bit by bit or byte by byte. So as we can see in the picture, the key is used to produce a stream of data. And this data is used to encrypt the message in a bit-by-bit manner or byte-by-byte manner. Here, the key can be produced using pseudo-random number generators. Examples of stream cipher is RC4. There are two common techniques that is used to construct ciphers. Ciphers means cryptographic algorithms. They are substitution and permutation. In substitution, letters of plain text are replaced by other letters. In permutation, the message is hidden by rearranging the letter order. So basically exchanging the position of the letter order. But Claude Shannon in the year 1949 introduced idea of substitution permutation networks. He suggested combining substitution and permutation to obtain diffusion and confusion. The diffusion is dissipates statistical structure of plain text over bulk of ciphertext. Confusion is it makes relationship between ciphertext and key as complex as possible. Claude Shannon 1949 paper has the key ideas that led to the development of modern block ciphers. Fiestel proposed the use of cipher that alternates substitution and permutation as a practical application of proposal by Claude and Shannon leads to the product cipher. So product cipher basically are two types, SPN and Fiestel. SPN is substitution permutation network. Block cipher principles. So this structure is Fiestel structure. In the Fiestel cipher structure, the data is split into two halves, left half and the right half. And it is processed to a number of rounds, which performs substitution and permutation. So the basic Fiestel cipher structure process 16 rounds. The LHS side of this figure shows the flow during encryption and the RHS in decryption. The process of decryption with the Fiestel cipher is same as the encryption process. Use the ciphertext as input to the algorithm. But use the subkeys Ki in the reverse order. So basically, the input is divided into left half and right half is sent through a function which is XORed with the key, and the output of the function is XORed with the left half to produce the right half. This right half is sent same as the left half. The whole process is Fiestel cipher structure. DES, Data Encryption Standard. It was adopted in the year 1977 by the National Bureau of Standards as FAPS Publications 46. DS encrypts data in 64-bit blocks using a 56-bit key. So basically, DS is a symmetric block cipher. Coming to the history of DS, in the late 1960s, IBM set up a research project led by Fiestel. The project concluded in 1971 with the development of Lucifer algorithm. Lucifer is a Fiestel block cipher that encrypts block of 64 bits using a key size of 128 bits. Later, to develop a marketable commercial encryption product that ideally could be implemented on a single chip, they produced a refined version of the Lucifer that has a reduced key size of 56 bits. So from 128 bits, the key is reduced to 56 bits to fit on a single chip. So in 1973, the National Bureau of Standards issued a request for proposal for a national cipher standard. IBM submitted the modified Lucifer and was eventually accepted as DES. So DES takes 64-bit blocks and encrypts using the 56-bit key. DES encryption takes input as 64-bit data and 64-bit key basically. So we can see the left side shows the basic process of enciphering the 64-bit data block. It consists of an initial permutation which shuffles the 64-bit input block and then 16 rounds and then again 32-bit swap and again the inverse initial permutation of the same initial permutation, which is the inverse. But the right side shows the handling of the 56-bit key. An initial permutation of the key which selects from 64-bit, the output of the permutated choice one is 56. And 16 stages to generate the 48-bit subkeys using a left circular shift and a permutation of the two 28-bit halves. So the first step is initial permutation. So this is the initial permutation. The initial permutation reorders the input data bits, even bits to the left half and odd bits to the right half. Let's take an example. If this is the data, then this data is converted to bits. This is the byte data. This byte data is converted to bits and shift the positions of the even bit positions to the starting and odd positions to the ending. So basically, we'll get this output. So the 58-bit will be the first, 50-bit will be the second, 42-bit will be the second, and so on. So this is the DS round structure. So one round of the DS consists of this whole process. In DS round structure, the input data is 64 bits, and after this initial permutation, we are getting one left off and one right off. So left off is here and right off is here. Let's consider Li minus 1 and R minus 1 is as current step, and Li and Ri as the next step. So Li is same as Ri minus 1, and Ri is a function of Ri minus 1 and Li minus 1. So basically, this whole process is called as function f. So this f takes 32-bit R half and 48 bits of key. So here we got 64-bit key, and it is sent to 56-bit key, and it is sent to left circular shift and permutated choice 2. So here it is 56. The key size of the bit is 56. So the 56 is divided into 28 and 28 bits, Ci minus 1 and Di minus 1. These are sent to left shift, and these are sent to permutated choice 2. We'll discuss later what is permutated choice 2 and the expansion table, all those things. And the key is 48 bits. So here Ri minus 1 is 32 bits. It is sent to expansion table, and this expansion table produce 48 bits. So this 48 bits is XORed with this 48 bits and produces one more 48 bits. This 48 bits is sent through substitution choice, and it produces 32 bits. So basically, there are 8 substitution box, which takes 6 input and produces 4 output. So which produces 48 bit, which takes 48 bit input and produces 32 bit output. So how are these S boxes calculated? All those things is classified. DS not published how they calculated all those things. So after this, it is sent to permutation. So basically, the bits we got is rearranged in this manner. 16 bit is first, second bit is 7 bit is second, 28 bit is second, like that. And this whole thing, the 32 bit whole thing is XORed with the left current step, Li minus 1 of this step. So we'll get Ri. This whole process will go on until 16 rounds. So basically, this whole function you can see as this thing. The right half of 32 bits is sent to expansion table, and this will get 48 bits. And the key is 48 bits. The whole thing is XORed, and this whole 48 bits is sent as input to the substitution box. We are having 8 substitution box, and each substitution box takes 6 inputs and produces 4 outputs. So we will get 32 bits, and this 32 bits is sent to permutation table. This the output is XORed to get the Ri part of the round. So how the DES key schedule is calculated? So we can see the DES. The DES is 64 bit. The DES whole algorithm takes key with key of 64 bits. So the key is 64 bits, and the key is arranged in this order, and the white part is removed. So we'll be left with 56 keys. So these 8 keys are removed. So we'll get 56 keys, and these 56 keys are sent to permutated choice 1. So permutated choice means just rearranging the position of the bit. So this permutated choice again is sent to permutated choice 2. So the schedule of left bits. So we can see there are 16 rounds in the DS algorithm. So for the first round, the bits rotated is 1. So 1 bit is rotated. 1 bit is shifted to the left. For the second round, 1 bit is shifted. For third round, 2 bits are shifted, like that. So first 56 bits or 64 bits are sent, and it got reduced to 56 bits, and these 56 bits are rearranged. And in the round, 56 bits are again reduced to 48 bits. And then we'll get the 48-bit key. This 48-bit key is XORed with the expansion table to get the whole process. So avalanche effect. So what is the avalanche effect? It is a desirable property of any encryption algorithm wherein if an input is changed slightly, the output changes significantly. As we can see, this is change in plain text, this is change in key. If I change 1 bit in plain text, 32 bits in the output is changed. After passing through IP 16 rounds and initial permutation inverse, the 32 bits are changed. So it is significantly more. So it is same as in the key. If we change 1 bit in the key in the first round, the 30 bits are changed at the output. So coming to strength of DES, the key length is 56 bytes. So 2 power 56 keys are possible. It's impractical to attack at the time in 1977 using brute force. Basically, brute force method is checking every possibility. That is, hacker sniffs the ciphertext and go on trying to decrypt with the 56 bits. That is 000 and so on 1 0 0 0 and so on 2 like till uh, till every key and so on until he gets a meaningful plain text. But in 1997, a large network of computers cracked DS in a few months. In July 1998, the Electronic Frontier Foundation announced that it had broken a DS encryption using a special purpose DS cracker machine that was built for less than $250,000. So the attack took less than 3 days. In 1999, combining DS cracker and a network of computers, DS cracked in 22 hours. So we need alternatives. Then triple DES comes into picture. So what is a triple DES? Triple DES runs the same DES algorithm in succession with three different keys. The process is encrypt, decrypt, and encrypt again. It uses three different keys. Like use first key to it can use three different keys or two different keys or only one key to for the whole process. It's like first encrypt with the third key, decrypt with the second key, and encrypt with the first key. And the second type is encrypt with the first key, decrypt with the second key, and again encrypt with the same first key. And in the third type, the whole three keys are same: K1, K1, K1. Like first they'll encrypt the plain text with the key 1, and again they'll decrypt with the key 2, and again they'll decrypt with the encrypt with the K1 to get the ciphertext. So why we need 3 DES? Why not 2 DES? So the strength of DES is 2 power 56 as we discussed. So the 2 DES has to become 2 power 112, right? So, but there is a issue here. Meet in the middle attack. So it is also known as plain text attack. So here the attacker knows one or more plain text ciphertext pairs formed with the secret key. So let's say the plain text is encrypted to get the ciphertext. Ciphertext is decrypted to get the plain text. Let's say we are using double DES. In double DES, we'll encrypt two times, one with key 1 and one with key 2. So plain text is encrypted with key 1 to produce X. The ciphertext is decrypted with key 2 to produce X. As we can see, these two X are same. So an attacker can take one plain text and the ciphertext produced with the key and go on brute forcing 2 power 56 times this one, 2 power 56 times this one, and check the output if X are same. If X are same, then K1, K2, he got the keys. So theoretically, it is 2 power 112. The strength of double DES is 2 power 112, but practically it is 2 power 56. So coming to triple DES, the strength will become to 2 power 112. AES. AES refers to Advanced Encryption Standard. Because of the DES security issues, clearly a replacement for DES is needed. We can use triple DES, but it is slow and has so many blocks. So US NIST issued call for ciphers in 1997. So 5 were shortlisted. So first 15 candidates accepted in June 98, but 5 were shortlisted in August 1999. They are Mars, RC6, Randall, Serpent, and Twofish. So at the end, Randall was selected as AES in October 2000, but it is issued as FIPS Publications 197 standard in November 2001. So AES, it is designed by Raymond Damon in Belgium. So it is a symmetric block cipher. It is an iterative or SP network cipher rather than Feastel cipher. So basically DES is a Feastel cipher, but AES is a SP network cipher. We'll talk about the difference between Feastel and SP a little later. So here it processes data as blocks of 4 columns of 4 bytes. It operates on entire block in every round. So basically the block size is 128 bits. So the input size is 128 bits. So there will be 16 bytes. So 16 bytes forms a matrix. So it processes data as block of 4 columns and 4 bytes. There are 3 types of AES: AES 128, AES 192, and AES 256. In AES 128, key size is 128, and number of rounds is 10. Here key size is 192, number of rounds is 12. Here key size is 256, number of rounds is 14. For all those things, the data size is 128. So here we can see the AES algorithm whole process. Every round has byte substitution, shift rows, mix columns, and add round key. First, the plain text is sent to add round key, and then the first round starts. It has substitution bytes, shift rows, mix columns, add round key. So every round has these four. So, but in the end, last round, there won't be a mix column. Same as for the decryption, inverse mix column won't be there in the last round. So here key is expanded in the form of words. So first round is byte substitution. So what is a byte substitution? In byte substitution round, the substitution bytes S-box in AES algorithm provides confusion in the ciphertext. So here basically each byte of state is replaced by a byte indexed by row left 4 bits and column right 4 bits. Let's say S0, 0. The first byte is 64. So it will check the S-box. 6 is first 6 box is row, means the 6th row, and 4 means column. 4 means column. So basically 64 results to 43. So the 63 is replaced by 43 here. So how this S-box is calculated? This S-box is calculated using Galileo's finite field. The second block is shift rows. In shift rows, first row is unchanged. Second row is shifted, circular shifted to left. So this is the second row. So S1, 0 is shifted left. S1, 1 is shifted left side. S1, 2 shifted left side. S1, 3 shifted left side, which is circular shift. So this S1, 0 comes here. So the first row is unchanged. Second row is circular left shifted by 1 byte. Third row is circular left shifted by 2 bytes. And fourth row is circular left shifted by 3 bytes. Decryption uses circular right shift. Here we are using circular left shift, but decryption uses circular left shift. Right shift, sorry. So the third block is mixed columns. Here each column is processed separately. Each byte is replaced by a value dependent on all 4 bytes in the column. Let's say this is a matrix. This matrix is also pre-calculated, and it is calculated using Galileo's field. So if this is my data, input data, and this is the matrix. In mixed column, every input data is multiplied with the matrix multiplied with this matrix. So let's say 02, 03, 01, 01. So this is matrix multiplied by this column. So 87 F2 4D 97. So 87 is multiplied with 02, and 6C is multiplied by 03, 46 is multiplied by 01, and A6 is multiplied with 01. So this whole thing replaces 47. So this is matrix multiplication. The fourth round is add round key. So we have to XOR the whole state, the output of the previous round, with the 128 bits of the round key. So basically, let's say key is 128 bits. So we are making bytes of 128 bits. So we get 16 bytes. So we can keep K0, K1, K2, K3. This whole things are 11 is 11 byte. So these are sent through a word. We'll get W0, W1, W2, W3. And this W3 is sent through a G function. This G function is this. So W3, if it is W3, then we'll take K12, K13, K14, and K15. B0 is K12, B1 is K13, B2 is K14, and B3 is K15. This is, the positions are interchanged and uses S-box. Previously we saw the S-box, right? Using this S-box, substitute the values to get B1 bar, B2 bar, B3 bar, B0 bar, and XOR with a round constant to get the W dash. So this W dash is, after passing W3 through the G function, we'll get W dash. This W dash is XORed with the W0 to get W4. So all the words are interlinked with the previous word. AES key expansion takes place for 128 bits, we get 44 bit, 32 bit words. For 192, we'll get 52. For 256, we need 60. So here we need 0, 3, means 4 words we need. So for the first, we'll get these 4 words. Till we'll get 44. For AES 128, we need 44 words. Till then, we'll process this word function. So coming to AES decryption, AES decryption is not identical to encryption since step done is reverse. Here, inverse S-box is used for inverse subbytes. So we have S box for byte substitution. For inverse byte substitution, we have inverse box. That is also pre-calculated. As we already discussed, circular right shift for inverse shift rows, and for mixed columns, we use the different matrix. Here we are using 0 to 0, 3, 1, 1, but here we'll use this matrix 0, 8, 0, B, 0, D, 0, 9. Basically, AES uses substitution permutation network, where data is divided into blocks and performs substitution and permutation. Whereas DES uses Feastel. It is both DES, both Feastel and SP network are the types of product ciphers. So in Feastel, the input is divided into two blocks, left half and right half, which interact with each other. But also SP ciphers require S boxes. Here is this the AES is a SP cipher. AES requires S boxes to be invertible to perform decryption. So here we need S box. For substitution byte we need X box. For inverse substitution byte we need inverse X box. So in Feastel, inner functions have no restriction and can be constructed as one-way functions. So as we discussed for DES avalanche effect, if we change one bit in the input, 58 bits are changed in the output after the round 10 of AES. Modes of operation. Any block cipher forms a basic building block which encrypts a fixed sized block of data. However, we need some way to encrypt arbitrary amounts of data in practice. So we'll get real-time data. So we need to encrypt or decrypt that data, not some blocks of data. To apply a block cipher in variety of applications, there are 5 modes of operation that have been defined by NIST. In essence, a mode of operation is a technique for enhancing the effect of a cryptographic algorithm or adapting the algorithm for an application, such as applying a block cipher to a sequence of data blocks, array, data stream, etc. So there are 5 modes of operation that are approved by NIST. They are electronic codebook, cipher block chaining, cipher feedback, output feedback, and counter mode. So what is electronic codebook? In electronic codebook, it is the simplest mode. The simplest mode is the electronic codebook, in which the plain text is handled one block at a time, and each block of plain text is encrypted using the same key. As we can see, plain text are divided into blocks, and they are encrypted using the same key. So the same plain text value will always result in the same ciphertext value. If my plain text are same for 1 and 2, I'll get the same ciphertext for as C1 and C2. If P1 is equals to P2, then C1 is equals to C2, right? So the term codebook is used because for a given key, a codebook of ciphertext can be created for all possible plain text blocks. So for example, I send Dora hacks here. So I'll get some ciphertext. So if I send this Dora hacks here, we'll get the same ciphertext. For a message longer than B bits, the procedure is simple. Just break the message into B bit blocks, padding the last block if necessary. So decryption is performed one block at a time, always using the same key. ECB is the simplest of the modes and is used when only a single block of info is need to be sent. For example, a session key encrypted using a master key. So if I want to send a key which is of single values, which is of not lengthy. So if it is lengthy, the plain text, if the plain text is repeated, we'll get the same ciphertext. So the attacker can get what is the key, what is the plain text, etc. So it's better to use the ECB only for less values. So the main disadvantage of ECB is message repetitions will show in the ciphertext. So cipher block chaining. To overcome the problem of repetition, we want some way to make the ciphertext dependent on all blocks before it. So here comes the cipher block chaining. So in cipher block chaining, it combines the previous ciphertext block with the current message block before encrypting. It will just XOR the previous ciphertext with the present plain text, and it will encrypt the produced data with the key to get the next ciphertext. The same thing will repeat. The input to the encryption function for each plaintext block bear no fixed relationship to the plaintext block. So therefore, repeating patterns are not exposed. To produce the first block of ciphertext, we need an initialization vector, and it is XORed with the first block of the plaintext to get, and after that it will be encrypted using the key to produce the ciphertext. So the initialization vector is a data block that is the same size of the message block, and it is generated randomly and is sent ECB encrypted. So we read that ECB can only be used to send the single values. So we can generate IV initialization vector using pseudo random generator, and we can send that initialization vector using ECB. The main application is it is used for bulk data encryption. So the advantages of limitations of CBC. So we need an initialization vector, and we need a way to send that initialization vector to the receiver. And here a ciphertext block depends on all blocks before it. So it can be advantage as well as disadvantage. It is advantage in the sense that if in ECB we came to know that the repetitions in the text can be shown, but if we use the chaining process, it won't be repeated. But the thing is, if there is a error in the ciphertext 1, then there will be error in ciphertext 2 and so on. So that can be a disadvantage. So the any change to the block affects all following ciphertext blocks. So that can be the disadvantage. So cipher feedback. So message is treated as stream of bits. In cipher feedback, message is treated as stream of bits. If we need to operate on smaller units like real-time data, we can use block of the data. But if we need to operate on smaller units like real-time data, we have to convert block cipher into stream cipher. That we can use using do using three modes like cipher feedback, output feedback, and counter mode. So in cipher feedback, the message is treated as a stream of bits. So as with cipher block chaining, here this is cipher block chaining. The units of plain text are chained together, so that the ciphertext of any plain text unit is a function of all preceding plain text. But in this case, rather than units of B bits, the plain text is divided into segment of S bits. The input to the encryption function, the input of the encryption function is a B bit shift register that is initially set to some initialization vector. Later, the leftmost S bits of the output of the encryption function are XORed with the first segment of the plain text P1 to produce the first unit of the ciphertext. So basically, IV is encrypted with a key to get the S bit and whole S bits. This B minus 2 this S bits is XORed with the plain text 1 to get the ciphertext which is of S bits. In addition, the contents of the shift register are shifted left by S bits, and C1 is placed in the rightmost S bits of the shift register here. So this process continues until all plain text units have been encrypted. For decryption, the same scheme is used, except that the received ciphertext unit is XORed with the output of the new encryption function to produce a plain text unit. So here we can see the both are encryptions. Here it is encryption and here it is decryption, but here both are encryption functions. The main application is stream data encryption, and here also we can see that errors will propagate. So that's why they came up with output feedback. So what is the output feedback? Here, the generation of the random bits is independent of the message being encrypted. We are generating random bits and encrypting and encrypting with a key, and we are XORing with the plain text to produce the ciphertext. So the output feedback mode is similar in structure to that of cipher blockchain, except that output of the encryption function is fed back to the shift register in OFB, whereas in CFB, the ciphertext is fed back to the shift register. Here we are feedbacking the part after encryption, but here we are feedbacking the part after the ciphertext. So the main advantage is that they can be computed in advance, which is good for bursty traffic. And secondly, any bit error only affects a single bit. That makes is good for noisy links. The advantages and limitations of OFP: need an initialization vector, which is unique for each use. So we need a nonce. Nonce refers to number only used once. So every time we need a nonce. The advantage is we can pre-compute it. Here bit errors do not propagate, and sender and receiver must remain in sync. That is the limitation of the OFP, output feedback. So coming to counter mode, unlike Here, each block of plain text is XORed with the encrypted counter. It is similar to the of OFB, but in OFB, we uses nonce and getting and the output of the encryption function is fed back to the next step. But in counter mode, the counter is sent to encryption function and counter will be incremented for every step. So we can use this for high-speed network encryptions. So the main advantages and limitations of counter mode is, unlike other chaining modes, encryption can be done in parallel. So execution of underlying algorithm does not depend on the input of the plain text. So if sufficient memory is available and security is maintained, pre-processing can be used. So here we can see nothing, the next part is not at all depend on the plain text and the cipher text. So we can just pre-compute the counter 1, counter 2 and store these here values, and later if we get the plain text, and we can use that data to XOR with the plain text to produce the ciphertext, or in the reverse manner. So here we can randomly access the encrypted block. So we can, if I want to access this block, I can randomly access that block. So it provides a good security. It is at least as secure as the other modes. But the thing is, we must ensure that we never use key or counter values. So we cannot reuse the key values. If key values are used, then it is prone to attacks. Thanks for your patience listening, and once again, thanks for giving me this opportunity. Thank you.